Question 19. A nucleus with mass number m is initially stationary. It undergoes alpha decay, emitting an alpha particle with speed v. The remaining nucleus recoils with speed w in the opposite direction. The system is assumed to be isolated. What is the speed w of the remaining nucleus in terms of m and v? This question tests our understanding of conservation of momentum in nuclear decay processes. So what do we know? We know that during nuclear decay, the original nucleus transforms into a smaller daughter nucleus with a lower mass number. When a particle is emitted from the nucleus, the remaining nucleus recoils in the opposite direction. This happens so that momentum is conserved. Because nuclear decay occurs extremely quickly, the system can be treated as isolated. That means no external forces act on it, so the total momentum of the system remains constant. We also know that an alpha particle contains 2 protons and 2 neutrons, giving it a mass number of 4. Now let's think through solving the problem step by step. Initially, the nucleus is stationary. Since it is not moving, the initial momentum of the system is 0. Because the system is isolated, momentum must be conserved. This means the total momentum after the decay must also be 0. Next, we define a positive direction. Let us take the direction of motion of the alpha particle as the positive direction. So the velocity of the alpha particle is positive v. The daughter nucleus recoils in the opposite direction, so its velocity is negative w. Now we write the momentum equation. The total momentum after the decay is the momentum of the alpha particle plus the momentum of the daughter nucleus. So we write m alpha multiplied by positive v plus md multiplied by negative w equals 0. The left-hand side represents the total momentum after decay from both fragments, while the right-hand side represents the total initial momentum for the initially stationary parent nucleus. Rearranging this equation gives m alpha times v equals md times w. Now we substitute the masses in terms of mass numbers. The mass number of the alpha particle is 4, so its mass is 4 mu. The remaining daughter nucleus has mass number m-4, so its mass is m-4 multiplied by mu. Substituting these into the equation gives 4 mu multiplied by v equals m-4 multiplied by mu multiplied by w. Now we rearrange to make w the subject. The unit mu cancels. Therefore, the speed of the recoiling nucleus is 4v divided by m-4. This is our final answer. What did we do? First, we recognize that the nucleus was initially at rest, so the total initial momentum of the system was 0. Then we used the principle of conservation of momentum, since the system is isolated. Next, we expressed the masses of the alpha particle and the daughter nucleus using their mass numbers. Finally, we substituted these values into the momentum equation and rearranged to obtain the expression for the recoil speed. Now let's address some common misconceptions. Some students incorrectly use the proton number of the alpha particle, which is 2, instead of its mass number, which is 4. This leads to an incorrect recoil velocity. Another common mistake is to correctly use 4 for the alpha particle, but forget to subtract this value from m when determining the mass number of the remaining daughter nucleus. The key points to take away. Momentum is conserved in nuclear decay processes because the system can be treated as isolated. The particles move in directions that balance the total momentum of the system. The mass numbers of the particles before and after decay must balance correctly. The recoil of a heavier particle is always smaller than that of a lighter particle due to mass differences. And because the daughter nucleus is much heavier than the alpha particle, its recoil speed is correspondingly smaller.